Hi everyone, week 10 summary. It's a pretty exciting week this week. We're covering some cool stuff. Starting off with inflation, which can be a bit of a tricky concept in some scenarios. Moving on to depreciation, we've got a straight line version and a reducing balance version. Then on to effective rate of interest, which is a very useful concept when you're comparing simple and compound interest options. We look at annuities, which are saving up, putting in money to the bank on regular intervals, and then looking at finally loan repayments, which is kind of the opposite of annuities, paying stuff off gradually over time. Cool. So let's look at the first thing, inflation. So first off, what is inflation? Well, inflation. I guess the kind of basic idea of it is it's you can kind of think of it as interest on everything. So it's the price of everything goes up. You know, when your grandparents might be like, "Oh, when I was a kid, an ice cream used to cost me 5 cents." Except that probably doesn't actually make any sense because they wouldn't have had cents back then. They probably would have had pennies. But anyway, if they did have cents, it probably would have cost them about 1 cent or 5 cents or something. So that's about inflation. It's not because ice creams are more valuable these days. It's because, you know, the price of stuff just goes up over time. So that's inflation. A kind of example, I guess, could be you could think about starting off with $1 at the start of the year. And say you get simple interest. So this is the start of the year. Got time going this way. 1 year. And you got simple interest of 50% on that dollar. So this is interest. Simple interest of 50% over 1 year. At the end of the year, you have $1.50, right? So now say we think about ice creams. Now, let's try and draw an ice cream cone. A beautiful ice cream cone. Say at the start of the year, our ice cream costs $1. So you can buy one ice cream. But over the year, we've got inflation, right? And that inflation might have within it, might raise the price of that ice cream to, oh golly gosh. So we start off with $1. It might raise the price of the ice cream to $1.20, say. So when we compare the start of the year, we say, sorry, that's strange things happening again. So when we look at the start of the year, what we can say is, how many ice creams can you get with your money? And the answer is 1. But then at the end of the year, you say, how many ice creams can you get with your money? And the answer is 1, and you got 30 cents left. And what we can ask is, if we didn't know about inflation, we would have said, well, 1 year at 50%, we'd got $1.50, we could get one ice cream and we'd have 50 cents left over. But due to inflation, we get one ice cream and we only have 30 cents left over. So, you know, it's the general price of things going up. That's what inflation is. And so we've got inflation and interest. It's confusing because they both start with the same letter, kind of sound similar in some ways, but they're different things. So the question is, how do we calculate inflation? Well, actually, it's really easy. It's exactly the same way as interest. We just start off. We just say our amount equals our principal, 1 plus inflation rate to the number of periods, inflation rate per period. And this is inflation's always in years, and the number of period, I guess we'll try and also keep it in years as well, because it's just compounding. You know, if you got time, cost, your ice cream starts at $1. Say you've got 20% inflation the first year, we go up to $1.20, 1.2, and then the next year we've got an extra 20% on that. So we're going to go up. The inflation on $1 would take us to $1.40, but then we need a fifth of 20 again, which is 4. So we'd end up with $1.44. The height of this is 144. So that's compounding. 1 year, 2 years. So that's inflation. What's next? Depreciation, straight line depreciation. Okay, so depreciation, straight line. And honestly, we don't really have to cover much here because all we've got is the amount is the principal minus depreciation rate and the number of excuse me, number of years. No of years, depreciation rate, and that's the decimal. And we notice that this is a linear graph, right? We could also write it as A equals negative dn plus p, which looks the same as y equals mx plus c. So it's just a linear. And you know, we start with our car is worth $1,000, and over time just decreases as it gets older. So that's our straight line depreciation. Really simple, basic linear stuff. So we don't have to spend much time on that. Next thing is reducing balance depreciation. So reducing balance depreciation, again, really simple. You've seen all this stuff before, and that's kind of a good thing about when we get to this end of semester. Things start to repeat, they just get called different things. So reducing balance depreciation, we start at the amount that it's worth today is the principal, what it initially started with, 1 minus I, and I in this case is the percentage loss in value per period, and is the number of periods. So you know, this one time value is going to go like this. And this is probably what your car does. You know, you buy a new car, it's worth heaps, 50 grand. As soon as you drive it out the door, bang, just lost 20% of what it's worth. Just really quickly, and then over time, you know, it kind of gets out and starts to flatten out. And so this is exponential decay, and we've seen this before. So again, linking it through to what we've seen before, and we've kind of got this y equals a b to the x thing, where a becomes just p, b becomes 1 minus I, and our x is our n. So seen it all before, no worries. Effective rate of interest. So here's the question to kind of get us thinking about effective rate of interest. What is better? ... We've got option A, 3.9% interest, simple interest, or B, 3.87% compound quarterly. Okay, well, let's work it out. The easiest way to work this kind of thing out is to say, well, let's think about $1 over 1 year. So let's think about option B. Option B, we start with $1 and we want to know how much we end up with. So the amount we end up with, if we start off with $1, invested at decimal 0.0387 over 4, because this turns it into annual. We're quarterly, which is our R over 4 gives our I. And then our number of periods is 4, which is 1 year. 4 periods, 1 year, compounding quarterly. What does that equal? Well, it actually equals, here's one I prepared earlier, 1.03926. Right, so that's how many dollars you end up with if you invest $1 at the start of the year. over 4 periods at this percentage per period, you end up with this. So how much in interest, well, we just take away the initial dollar, right? Therefore, the interest equals 1.03926 minus 1 far out Brussels sprout. So equals 0.03926, which is approximately 3.93%. So how does that compare to this one? Well, it's better. Therefore, B is better than option A. But hold on, let's have a look here. What we did was we took $1, so we can actually kind of forget about this one, right? Doesn't really need to be there. So what we had was A, and then our 1 plus I to the n, and then what we did was we took away the 1. And by taking away the 1, we changed it into effectively, that keyword effective, a simple interest rate. So we can generalize that to the formula E equals 1 plus I to the n, imagining there's a dollar, take away that dollar in the first place, and this converts compound interest to simple. Make sure your I is in a decimal form, and make sure your number of periods is adds to 1 year. So this is actually the effective interest formula that you would have seen, but we just worked out where it kind of comes from. What is next? Oops, I did that in the wrong color. Interesting. Oh well. Okay, annuities next. Number 4. Annuities. Okay, so annuities, we're talking about paying DOSH periodically, i.e. regular basis. So this is like, okay, if I put $50 into the bank every week for a year, how much would I have at the end of the year? So the end of the year is the future value. The future value is the amount we put in every period. So amount deposited per installment. And then we've got our 1 plus I to the n minus 1. That looks a lot like our effective interest rate over I. I'm not going to go into the derivation of this one because it's probably a bit much, but just remember that this I is interest rate per period as a decimal, as per usual. Okay, and so, but we can kind of think of this as another way. The question might say, what amount would you have to put in every period if the interest rate was X, or if the interest rate was I, or a given number? If the interest rate is 3% and you're compounding quarterly and you're investing for 1 year, and at the end of the year you want to have $1,000, how much do you need to put in every payment or every period? So I should actually point out here that n is the number of installments. No of installments. So, i.e. periods. So say you're investing for 4 periods, interest rate per period 3%, and you want to have $1,000 at the end. What's M? Okay, so sometimes we'll need M by itself, and we can notice that all we've got here is future value equals M times something. Then we can just divide both sides by something, and we end up with future value over something equals M. So that's how you manipulate that equation, just to get M out by itself. And that's pretty much all you need to know for annuities. Oh, that's the future value of annuities. But we also need to know about present value of annuities. And basically what we're asking here is, when you put money in, you say, okay, well that's great, you know, I've put $50 in every week for a year or whatever, but what I end up with at the end, what's that actually worth in today's dollars? So we can kind of think of this as the amount, today's dollars, is principal 1 plus I to the n. So we're saying, okay, so I use this annuity thing where I put in money all the time, but what if I had just put in a big lump sum, P at the start, to get the same future value? So similarly, we can say future value equals present value 1 plus I to the n, because we know that in this compound interest formula, the P is the principal, the present value, the present principal, the amount that we're putting in today, and A is the amount you get in the future, so the future value. So they're just the same thing. And so if we want to know the present value of an annuity, first we work out the future value, and then we just divide both sides by 1 plus I to the n. And so we have that present value equals future value over 1 plus I to the n. So that's what we can say if the question says, so what this annuity, what's this equivalent to? What's this annuity equivalent to? What would you have to, or in today's dollars, what's the present value of it? And that's the answer. You can just use this formula. Okay, finally, loan repayments. So loan repayments. Essentially here, we'll just let the answering machine do its thing, and we'll say M equals L I 1 plus I to the n over 1 plus I to the n minus 1. And again, this is our effective interest rate. Looks familiar. We've got our kind of B term here, our compounding term. And then what's L? Well, L is the loan, which we can kind of think of as the amount borrowed. And M is our repayment amount. And our I is the same thing. It's as it was up here, our interest rate per period, and our N is the same thing as it was up here, the number of periods. So this is just kind of like a reverse, kind of a reverse way to think about it. So we start off, we say, given that we've borrowed this much, we're dealing with this many periods at this interest rate, what is the repayment amount going to be? And I mean, I haven't explicitly said this in the past, but this I is this I is this I. So if our interest rate is 3%, we're going to put 0.03 here, we're going to put 0.03 here, and we're going to put 0.03 here. And if we're dealing with 3 periods, we're going to put 3 here and 3 here as well. So we haven't explicitly said that, but hopefully you kind of understand that those things are the same thing. So that's what you covered in week 10. And as I said, really, you know, we're making those connections to say that, okay, well, this inflation, you know, that's just a growth question. We can just use the compound interest formula. This depreciation, well, we've just got a straight line equation, y equals mx plus c, where m equals negative d in this case. Reducing balance. Okay, well, that's just exponential decrease, which we've already seen before. Effective rate of interest. What was that? E equals our b minus our 1. So that's really easy because it's just the same as saying, okay, we start off with $1 for 1 year, take away the dollar you had in the first place, and how much interest did you make? And so that's converting from compound interest to simple interest. Annuities, again, putting money in periodically, how much you end up with, and then moving back through the compound interest equivalent formula to get to the present value, today's value of what we're up to, and then looking at loan repayments. And that was just kind of a bit of a full-on equation, but driving it's not too hard. Just answering questions like, if you borrow $10,000 today, you're paying back at an interest rate of 5.5% per year, and you want to pay it back over 7 years, how much would you have to pay back every year, which is M. So yeah, week 10. Hope it all makes sense.